Hello, my name is Nadia and today's topic is on ocean ion fertilization. So let's get started on what ocean ion fertilization actually is. Ion fertilization is the intentional introduction of iron into iron-poor oceans to stimulate and increase phytoplankton growth and production on the upper layer of the ocean. Now, let's get on with the history of ocean ion fertilization. It started with scientists trying to figure out ways to reduce the negative outcomes from the beginning of the Industrial Revolution. Various ideas was formed and soon categorized into two categories, which was enhancing carbon dioxide uptake and controlling solar radiation by aerosol injection into the atmosphere. The most attractive method was ocean fertilization, and the general idea was that ocean fertilization could stimulate phytoplankton growth to export carbon to the deep oceans or sediments through ocean biological pump. So, why with the biological pump? Biological pump is the process of transforming dissolved inorganic carbon, DIC, into organic matter by phytoplankton and pumping the particulate form organic matter to intermediate or deep waters with hopes of carbon sequestration. Then, in the early 1990s, John Martin proposed the iron hypothesis as he understood that iron acts as an essential micronutrient to stimulate intake of other macronutrients by phytoplankton. Ocean ion fertilization hypothesis took a high interest by scientists only because only a small amount of iron with carbon to iron ratios of 100,000 to 1 can stimulate a strong response by phytoplankton even in high nutrients and low chlorophyll oceans, HNLC. In 1993, the first ocean ion fertilization experiment was conducted on October 1993 in the equatorial Pacific Ocean. So, how did Martin come to this? John Martin is a scientist and director of Moss Landing Marine Laboratories, who spent his career measuring trace metals in the ocean and found out that iron was present in very low concentrations in HNLC ocean zones, such as subarctic North Pacific, equatorial Pacific, and the Antarctic Ocean, where there was low phytoplankton available. This is a history timeline of how the hypothesis was proposed. He later found out that the only way iron was available in these areas are by winds of dust that blew over the ocean. In 1989, Martin sent out 3 lab technicians on a research cruise for a small-scale experiment to the Antarctic Ocean in order to test out his theory that if adding iron to seawater would increase phytoplankton growth, and the result proved his theory. Phytoplankton swarmed and clouded the iron-filled seawater and consumed all the nutrients available. Several months later in 1990, he had his hypothesis publicized. And finally, in 1993, scientists decided to test out his hypothesis. And now with some background on iron hypothesis, what is the objective on it? First, it is to increase phytoplankton growth by increasing uptake of macronutrients. Second is to induce phytoplankton blooms in high nutrient, low chlorophyll areas. And finally is to reduce atmospheric carbon by carbon sequestration through the biological pump. Before Martin started out on the iron hypothesis, he measured and analyzed trapped air bubbles in the Antarctic ice cores and found out that it had ancient air composition dating 20,000 years old back during the last glacial maximum. The atmospheric carbon dioxide was much lower compared to the industrial times now, where it had increased from 180 parts per million to 280 parts per million. In other studies, scientists also identified Earth's original atmosphere was rich in methane, ammonia, and water vapor, however lacked in oxygen compared to current atmosphere. They identified gas composition by analyzing bubbles of liquids and rock salt that contain trapped air. It was performed by carefully crushing the rock salts in order to release the trapped gases and using a mass spectrometer for analyzing gas components. And now we're moving on to the location for ocean ion fertilization. To test out Martin's hypothesis, the experiment was separated into 2 different ocean ion fertilization experiments that are artificial ocean ion fertilization and natural ocean ion fertilization. Areas chosen was focused onto high nutrient, low chlorophyll areas where there were lower phytoplankton densities. By using satellite imagery, They were able to identify high nutrient, low chlorophyll oceans located in North Atlantic, Equatorial Pacific, Subarctic North Pacific, and also the Southern Ocean. These areas were chosen due to primary production in the area to be relatively low, considering there is an abundance of macronutrients such as phosphorus, nitrogen, and also silica. From the diagram, this shows the worldwide map of the location chosen for each experiment. The different colored circles indicates the different phytoplankton available in the area, such that in the Southern Ocean, multiple orange shows that the most abundant phytoplankton presents are diatoms. Now, I would like to talk about the iron-climate relationship. In normal conditions, atmospheric carbon dioxide is dissolved into the ocean and turns to dissolve inorganic carbon. Through upwelling processes, nutrients are carried up from the deep ocean, fertilizing the ocean surface water, thus providing macronutrient source for phytoplankton. Photosynthetic processes performed by phytoplankton will absorb, dissolve inorganic carbons and nutrients available, producing organic matter and oxygen as a byproduct. When the organic matter decomposes, it is transported to the ocean depths through ocean biological pump. The effectiveness of transferring organic materials through biology pump depends on the uptake of macronutrients. Based on iron hypothesis, inputs of iron will stimulate more intake of dissolved inorganic carbon and macronutrients by phytoplankton. Hence, more carbon dioxide is removed from the atmosphere as there are also larger blooms of phytoplanktons. Besides that, higher intake of macronutrients will increase phytoplankton growth and abundance, thus more carbon dioxide is absorbed. Now, how many experiments have been performed so far to study ocean iron fertilization? A total of 6 natural ocean iron fertilization and 13 artificial ocean iron fertilization experiments were conducted within the span of 21 years, beginning from October 1993 with experiment Ironex 1 and ending with Lohafex experiment in March 2009. During these experiments, limitations were faced that contributed to unsuccessful findings. Experiments studied in the Equatorial Pacific faced insufficient experimental duration to observe full phase of biogeochemical responses. Next, micro and macronutrient limitation and also subduction of fertilized patch. Experiments in the Southern Ocean faced light limitation by storms, insufficient experimental duration, and also high dilution rate by small patch size. And finally, limitations faced by experiments held in the subarctic North Pacific are single iron addition and also insufficient experimental duration. Now, here comes the next question. Was the experiment a success or not? The introduction of iron into ocean by iron fertilization have resulted to increase of primary productivity and decline in macronutrients and dissolved inorganic carbon. However, the overall results from experiments conducted on ocean iron fertilization did not meet the expected outcome and success to remove carbon from the atmosphere and increase carbon sequestration. Instead, other problems arise after the introduction of iron into study areas such as decline in oxygen content. Furthermore, continuous iron fertilization to increase carbon sequestration would deplete other available macronutrients such as phosphorus, nitrate, and silica that hence prevent growth of phytoplankton. Based on results from Equatorial Pacific, Iron X1 showed lower biogeochemical responses than expected. From the Southern Ocean, SOI-RE showed no measurable changes in the carbon export, and from the subarctic North Pacific, there was no detection of carbon fluxes. Thus, the experiment conducted were considered as a fail as it did not meet the objectives. Now, in order to improve future experiments, limitations faced during the first 13 experiments should be taken into account. The first thing to consider is to determine an appropriate location with lower possibilities of limitation. From the previous experiments, grazing of diatoms by mesozooplankton disturbed photosynthesis process which affected results. Hence, to accommodate, future experiments should be located in areas with high silica as macronutrients and low grazing mesozooplankton. Next, timing is a very important factor to consider it. Obtaining results such as low primary productivity due to limitations like low light availability can be avoided. Setting the correct time to conduct iron fertilization experiment is also able to make sure that there is availability of nutrients in the study area. And finally, strategy and approach in maintaining and adding iron into the ocean. Since high quantities of iron will be used, an interval of 10 to 15 days after each iron fertilization can prevent iron limitation during the experiment. Besides that, a more environmental and better approach should be considered and planned to prevent other complications that can limit phytoplankton growth. And finally, we should also consider having a strategical backup plan to avoid limitations that could prevent us from reaching our main objective. And that is all from me on ocean iron fertilization. Thank you and have a good day.